This presentation is based on the PhD research that I conducted with Dr. Wesley Marshall, and the title is Evaluating Sidewalk Infrastructure and Prioritizing Investment. So to get started, we'll dive right into it. So what is the purpose of this research? Well, first off, when we did our evaluation of prior research, what we found is that the literature tends to show that sidewalk geodata is scarce. And this is common. We saw this in numerous research papers. And in addition to the scarcity of data, we also saw that the analyses that were conducted based on sidewalk geospatial data is also very limited. So going beyond even just the academic literature, when we were looking at pedestrian plans, and this is a great example using Milwaukee, we were seeing that cities were also running into trouble with not just the data, but we could also see that part of the issue was a lack of funding to assist them with this. And of course, there was also the lack of data in turn because of the lack of funding, or in part because of the lack of funding. And as you can see here, they specifically point out a lot of pedestrian infrastructure such as sidewalks and curb ramps. So what we did was we incorporated the use of spatial data and big data in our research to help fill this gap, this academic gap, as well as the issue to help with the issues that we were seeing cities are running into as well. So to get started, the first thing we had to do was have a better understanding of sidewalks and sidewalk data itself and find out what was available. So what we did was we turned to what's called planometric data. So a real quick overview of what planometric data is. You can see in this picture here, basically what it is aerial imagery. And then from that aerial imagery, you're able to basically trace a two-dimensional representation of infrastructure. So here you can see in yellow, you can see your building outlines, and they also have this data for sidewalks. So the reason why we wanted to make use of this is it's noted very well here in prior research as well that GIS and geospatial data is almost necessary to be able to analyze and gain a better understanding for large areas. So we wanted to use the geospatial data to have a better understanding of sidewalks at the city scale. Now, the reason for this is also because prior research tends to show that they meaning the prior research that's being done, is only looking at small sections of cities. So we're seeing neighborhoods, maybe a couple streets, a couple blocks, but not the city in its entirety. In addition to that, when researchers wanted to have a better understanding of the city as a whole, what we were seeing was they were using other data, such as roadways. And as we know, roadways do not necessarily mean that sidewalks are present. So that's somewhat of a skewed approach. So what we did was we looked at every single US Census place at that time period, which was in 2018, and there were 769 census places with a population of 50,000 or more people. So when I say that we researched and looked into all 769 US Census places, it wasn't as direct as you just go check the city and they either do or do not have a sidewalk data set. It was a lot more complicated than that. We had to check from different angles. So we had to look at county data sets. We had to make sure that we were taking a look at the attributes that were being provided in the data to make sure that it had what we needed. We also had to check for different naming conventions that were being used, or just different names, I should say, that were being used by cities and counties, such as paved areas, as you can see here. So it's not directly stating sidewalks. And some of them even had them organized in places where you may not expect it to be. So here under the structure grouping of data is impervious surface for Corvallis, Oregon, and that is actually where their sidewalk data is located. So it was definitely not a straightforward method for us to try to identify who had sidewalk data across the United States. In the end, we had 24 viable cities with data that we could use in our analysis. And what this does is viable data, meaning that these cities had enough to go from what was those small areas of the city to now we can research the city in its entirety. We can actually research all of the sidewalks in the entire city. So let's take a look at what planometric data looks like. So here's an example of what a planometric data set may look like. You have your buildings, sidewalks, roadways, lots of other components that we needed to remove because our interest is just the sidewalks and the roadways. Beyond that, we still had to find a way to contain that data so that when we're looking at all these cities, we're looking at it from the same standpoint, which is essentially we wanted to be able to isolate sidewalks and roadways that are within the right-of-way. So by using parcel data, as you can see here in blue, we were able to isolate the sidewalks and the roadways in all of these cities. So what we did was we took a look at sidewalk availability, which is basically taking the linear data of the center line for the sidewalks and the center line for the roadway and calculating availability. We did the same thing with average width, which is just, as it sounds like, taking a basic calculation of the area divided by the center line length for the sidewalks, and we were able to calculate an average width. So the average width is helpful, but we needed to compare it against something. So we took a look at different standards that are available. So the ADA is kind of its own in the sense that the ADA is a law. So the 2010 ADA standards are a law, so that 3 foot is a little bit different. But in addition to those standards, we looked at other recommendations from other agencies such as AASHTO, FHWA, so on and so forth. In addition to looking at availability and average width, we looked at sidewalk land coverage. So sidewalk land coverage is taking a look at the relative comparison within the right-of-way of your sidewalks and how much area is taken up within the right-of-way compared to how much of that area is taken up by the roadway. So this is an example of some of the results that we came up with. Sometimes it's better to give a graphic example because it shows it a little bit better. You can understand a little bit more of what we came up with. So a city with a high overall sidewalk width, you can see here in Peoria, Illinois, the city is fairly well saturated with sidewalks that are much wider, as opposed to when you look at Cedar Rapids on the right-hand side, it's somewhat clustered and limited with those wider sidewalks. Same thing here is an example of sidewalk availability and what our results look like. On the left in Corvallis, you can see the majority of the city pretty much has sidewalks, as opposed to Lynchburg, where once again, it's very isolated. There's just some clusters and sections, more than likely in the downtown and maybe along main streets where sidewalks are available. So what did we find out overall? Basically, there's a deficiency in sidewalk availability in cities. So more specifically, what we mean by that is on average, there's about 50% sidewalk availability, which means if you think about it, that there are basically sidewalks only on one side of the roadway, not on both sides, which can lead to very dangerous scenarios for people who are trying to walk or roll from point A to point B, as you can see in these examples here. In addition to that, we found that just over 10% of these sidewalks failed to meet the ADA standard, which is 3 feet. So once again, these are good examples in these photos of what that actually looks like if you're thinking about it from the standpoint of being a pedestrian. And when we looked at land coverage, the comparison of land that's covered by sidewalks compared to land that's covered by roadways, this picture kind of encompasses what that looks like. 12% on average was sidewalk and 88% was roadway, which is a pretty common sight. I'm sure everybody can look at this and kind of shake their head and say, yeah, this looks pretty familiar. It's pretty much all roadway. So now that we have been able to identify cities with sidewalk data, and we've had the ability to understand how to derive information from that data, the next thing we wanted to do was take a look at obstructions in sidewalks. So when we download sidewalk data, that planometric data, it gives the impression that this is what sidewalks look like. There's nothing in the way, there are these perfect sidewalks in your city, but the reality is that's not what it looks like. We all know that walking along sidewalks, there tend to be obstructions, something that gets in the way. So to conduct this part of the research, we looked at Cambridge, Massachusetts. Here's an example, just an image of what the planometric data for Cambridge looks like. Cambridge had an excellent data set, not only for their sidewalks, but also for obstructions that we could make use of in the data set for the analysis. So let's zoom into that yellow circle here to give you a better idea of what this looks like. So when we downloaded the original sidewalk data, this is what it would look like. So you get these very clean and clear looking polygons where it would seem as though these are great looking sidewalks. When in reality, when we also included the static obstructions, you get a very different visual now of what it would be like to be a pedestrian walking down this sidewalk. So let's zoom in even closer now and take a more specific look at what this looks like. So in that section that we zoomed into, it's essentially a 5-foot wide segment of sidewalk, which would sound great if you're, two people walking side by side, a person walking in a wheelchair, a delivery person. You have 5 feet of width, so you have plenty of space to get by. But once you incorporate those obstructions, you have a very different understanding of what that sidewalk looks like. Now, all of a sudden, you have an obstruction in the dead center of that sidewalk, and now you only have 2 feet to actually get by. So I want to be more clear in terms of what we're talking about when we say static obstructions. When we talk about static obstructions, what we're saying here is we're taking a look at street trees, we're taking a look at benches, we're taking a look at lighting, we're taking a look at garbage cans that are on the side of the road. And in total, there were over 30,000 of these features in sidewalk polygons in the data set. So the methods and the approach that we had to actually deriving this information and gaining an understanding of how these obstructions impact the ability for pedestrians to walk in these sidewalks. What we did was we looked at every section where there was an obstruction, and we wanted to say, okay, so in this example at point A, where there's an obstruction, you have 2 feet is the maximum width to get around that obstruction. That's the optimal choice that a pedestrian would have. You would want to take the route where you have the widest area to be able to navigate around it. We also took a look at the width of the sidewalk itself. So in this example, you have 5 feet. And lastly, we took a look in this example at, let's say, where the other obstruction existed, and you have 4 feet of space to get around that obstruction. So in the end, we said, and we did this for every single polygon in the city of Cambridge, we said, of those, what's the pinch point? What's the narrowest point along this polygon for a pedestrian? At point A, where you have only 2 feet to get around that obstruction. So once again, this is our method and approach to find that pinch point of how to get around these obstructions and how much width you actually have as a pedestrian when walking along the sidewalks in the city. So the results that we found were that the number of compliant sidewalks, meaning those that were ADA compliant of 3 feet or greater, was cut nearly in half when we accounted for static obstructions. So let's take a look once again at some graphic examples of what this looks like. So in this example on the left, this is Cambridge, Massachusetts, and this is what it would look like for sidewalks that are in compliance with, this would be the ADA. So when we incorporate the static obstructions, that drops considerably from 78% to 51%, which is a 34% difference. And we did the same thing for the 4, 5, and 6 foot. So let's take a look at 4 foot here. Without static obstructions, it looks like there are 59% of those sidewalk polygons that are compliant at 4 feet. And when we incorporated those obstructions, it drops to 31%. That's a difference of about 48%. At 5 feet, 36% without obstructions, 18% with obstructions, which is just about 49, almost 50% difference. At 6 feet, without static obstructions, we were at 17%. With static obstructions, we were at just about 11%. That's a 39% difference. So we basically found out that static obstructions do account for a considerable difference in the sidewalk width. So lastly, we said now we have a better understanding of what cities have sidewalk data available, planometric sidewalk data. We're able to derive information from that to learn more about our infrastructure. So how can we put this to use? How can we give this a practical sort of use? So in this last section of the research, we looked at how to prioritize sidewalks.
Yeah,
So
5 minutes left.
in this, what we did was we took a look at the city of Denver, Colorado. And Denver currently has the neighborhood sidewalk repair program. Now, this has been going on for a number of years, but unfortunately, this is still what the sidewalks look like throughout Denver. Not doing so great. So, they have the right idea that they have this program in place, but the sidewalks are still in very poor condition and they're having trouble with what this program is actually achieving. As a result, this is what ends up happening. People find their own way. They no longer use the sidewalks if they're in poor condition. And these basically are dangerous scenarios once again. This is a safety issue. This is a concern for the city. And on top of that, we're also finding that there are cities that are facing legal ramifications because of this. The ADA, once again, is a law, which gives groups and people leverage to essentially go after the city. And as you can see here, there are numerous lawsuits that have come about in cities across the United States. So this is something that cities are interested in, not just because of the legal ramifications, but also because they're obviously trying to do something to fix this, to rectify the problem. So here's a good example of what is actually happening. We have an audit that was conducted in November 2020 for the city of Denver and their sidewalk repair program. Essentially what they're saying—
You have 2 minutes left, Nicholas.
I'm sorry?
You have 2 minutes left, Nicholas.
Okay, thank you. So basically what they're saying is, at its current pace, it's going to take more than 50 years to complete, which is being generous, to be honest. And they're saying that there's issues with the data collection. So when we also dug into what the literature said, we're finding that there's still a lot of manual data collection that's taking place. So what we did was we incorporated the use of big data. So data from cell phones and from GPS tracking devices on vehicles. And this is made available from street-light data. So street-light data gives us basically origin zones and destination zones that we were able to look at throughout the city of Denver. So we looked at all 476 traffic analysis zones in the city. We looked at short vehicle trips as well as all pedestrian trips. In addition to that, we also normalized the data by the population so as to make sure that we were not overlooking any TAZs that had a small population. And here's a great example of one TAZ that went from 64th to being ranked second in the city based on the number of trips that were taking place. And our focus was on the origin TAZ, because if you can't even start your trip, then what's the purpose? That's where the main problem is going to be that we wanted to focus on. We used the sidewalk polygon data from Denver Regional Council of Governments through the city. And we came up with a data-driven prioritization. First, we said which TAZs have the most short vehicle or pedestrian trips. Then we said, after that, let's take a look at those And is sidewalk infrastructure design an issue in those TAZs? If not, is it maintenance? And if not that, what else could it be? So let's take a look at the first one. Basically, for TAZs that show vehicle trips of 1 mile or less, and for pedestrian trips, all pedestrian trips, we found 32 TAZs that rank the highest, which are these. So the second question, which is, let's take a look at those 32 TAZs, and we found 21 that had sidewalk design issues, which leaves 11 TAZs remaining. Next, we said, well, if it's not infrastructure design, is it maintenance? We found 8 that had sidewalk infrastructure maintenance issues. And then of those, I wanted to show at least one example of what we mean by maintenance issues. So overall bad condition of sidewalks, poor crossings, or just missing curb ramps. So that left 3 TAZs remaining. So if it wasn't any of the above, what else could it be? So another factor we identified was that it could just be the intersections. So of the 3 remaining TAZs, if you look here, this is an example of what those intersections tend to look like on the boundaries of these TAZs. That could also come into play. And then there was one where we couldn't
Nicholas,
find
I
any
hate to
apparent
do that,
reason,
but I
we were
have to
able
stop
to
you
narrow
here.
it down. So in the end, basically, we have all of this amazing data, but we have to remember it's still about the people. So with that, I want to say thank you. I also want to say thank you to the National Center for Transportation Infrastructure, Durability, and Life Extension, as well as the universities for their support. Thank you.